This is lesson 2 of our chemical energy unit. In this lesson, we're going to focus on what makes a hot object hot, as in how are its atoms and molecules behaving differently than in cold objects. And of course, atoms and molecules we may refer to as particles occasionally, but it really has to do with those, and that's why we wanted you to do that simulation before you came to this lesson. The other thing we're going to focus on a lot today is we're going to look at how heat is gained or lost. And you remember from yesterday's lesson that we abbreviated heat Q, and we decided whether heat was gained or lost and applied a sign to it. Like for instance, do you remember if heat is gained, if you're gaining heat, is that positive or negative? Well, it's positive, right? And heat you lose is negative. And of course, it all depends on which perspective you're talking about. We're assuming that you're interested in a certain system. But today we're going to look at phase changes. And what we mean by phase changes are like evaporation or condensation. Melting is a good common everyday one. And we're going to figure out whether those objects that are melting and evaporating are gaining or losing heat. So if you think about it yesterday, we said that the ice cube was cold and the water was warmer when you first put in the ice cubes. Now, based on the experience you had yesterday, do you think the particles, the atoms inside this ice, are moving fast or slow compared to the atoms in the water or the molecules in the water? Which of them are moving faster? Well, there's no doubt that the atoms in the ice are moving really slowly. That's kind of what we saw yesterday, that the warmer things are, the more they're moving, the more they're vibrating. So what we were exploring yesterday was how do the atoms in hot objects differ from those in cold objects? And speed is a big part of it. Let's go look really quickly. I've got a, we'll say discard. Let's go look really quickly at that PhET simulation, right? We saw that when atoms were really cold, like that's very cold, you warm them up and they start moving faster, right? But if we stick just with gases, the hotter we make them, the faster they move. They start speeding up and speeding up and speeding up. And that's true whether they're solid, liquids, or gases. But that's what makes a hot object hot, is the atoms are moving faster. If you cool it down, they move slowly. Oop, that didn't change it much. It's all the same temperature. Anyway, you've explored this idea. So if you understand that, then we can move on and figure out how phase changes can be predicted with what you learned yesterday. All right, so let's get into how can we use our understanding to predict whether heat is gained or lost in phase changes. Well, it can be a little tricky to figure this out, and the one thing I'd recommend you do is don't just guess at it, draw some particles. So thinking about those particles and those atoms can help a lot. Like let's look for instance at this puddle that's sitting in the sun. So, you know, the sun is out really bright today, maybe it rained yesterday, and the sun is shining on that puddle, and this thing is evaporating. The water is evaporating. Now, you can hear me talking an awful lot about the water, which must mean I think the water is the system. Now, if you think about the particles in the water, right, those water molecules, you know, they're not super tight together and they're not super organized like they would be if they were ice, right? They'd be really close together. And they're moving a little bit. You know, they're kind of wiggling, sort of like that. But they're not wiggling as fast as if they were a gas. As soon as they start to evaporate because things are getting hot and they go up into the air, those gas particles are really far apart now that they're in the sky, right? As they evaporate, and they are moving fast at this point. So the thing that we know is these are moving slower when they're in water form, and they're moving faster when they're in gas form. They have more energy when they're a gas, and they have less energy when they're a liquid. So what that means is if you're going to turn them into from a liquid into a gas, they must have to gain energy. And if they have to gain energy, do you think that's endo or exothermic? Well, it's definitely endothermic because they have to gain energy. The sun's energy has to come into these particles to make them go faster, because we know that gas particles just flat out move faster. So they have to gain energy to do that. So drawing these little particle diagrams can help us figure out that evaporation is endothermic. Now, if you would have said this water is boiling or something else and you didn't know the word evaporation, well, don't worry about that. At the end, we're going to summarize all the phase changes. But let's try another one. If we look at this one, you can see that in this example, a liquid is turning into a solid. Well, what kind of phase change do you think is happening here? If it's a liquid turning to a solid, that's freezing, right? We had a liquid water underneath this ice and it froze, so that's an example of freezing. And it seems like there should be a fancier science term than that, but it really is just called freezing. So if we were going to try to figure out, is Q positive or negative here during this phase change? And is it endo or exothermic? The answer is, don't just guess at it, draw some particles. So how would we draw the liquids? Well, the particles would be not quite as close together as they are over here in the solid. They're a little bit further apart. And which of these two do you think would be moving faster? Well, solids their atoms hardly wiggle at all. You remember in that simulation, they were wiggling a little bit, but not much. But when they become a liquid, they can move quite a bit more. There's more energy, more wiggle energy here. There's less wiggle energy in the solid. So that means, does it have to gain or lose energy to become a solid? Well, if you said it has to lose energy, you are correct, which means it's losing heat. So, positive or negative? Well, if it's losing heat, that's like money coming out of your wallet, it's negative. And if it's losing, the heat must be exiting these particles, so I think it's exothermic. So freezing is exothermic. And it's amazing how just looking at the particles and thinking about which ones are wiggling more, are the liquids or the solids wiggling more, can help you figure out whether they have to gain or lose energy. Whenever you have a phase change, draw a particle diagram. So if we look at this one, somebody's drawn a great one for us. If we were going to guess what phases they are here, because they're not really labeled, right? I mean, we look at that last one, they were labeled. These aren't really labeled. Well, the ones on the right are really far apart and moving really fast. I think these are gas particles. And these are really organized in kind of a rigid matrix. They're hardly moving at all. I think that's a solid. So a solid is turning into a gas. And if we were going to say what phase change this is, well, this is the hardest one. Most people don't know this one, but you might. This one is referred to as sublimation. And like I said, if you don't know all the phase changes, don't worry, we're going to summarize them at the end. But I have a feeling you might actually have seen this happen before. Because in sublimation is most commonly seen in dry ice. If you've ever been to the grocery store and gotten dry ice from like King Soopers or Safeway, some people like to use it to keep things cold for a long period of time. But dry ice, which is actually, I think it's CO2, dry ice turns directly from a solid into a gas without ever becoming a liquid. It just gone. So it's pretty cool. So you can see, I think that sublimation is endothermic. How do I know that? Well, not by guessing. I look at the particles. Are it the solid particles or the gas particles moving faster? Well, the gas particles are moving much faster. They have a lot more energy in them. These are moving much slower. They have much less energy. So if you're going to turn these slow wiggling particles in the ice here into faster ones, you're going to have to add energy. Well, if you add energy, is that endo or exothermic? Sounds like heat is entering to me, so therefore it's endothermic. Is Q positive or negative? If it's absorbing the energy to go faster, it's got to be positive. So there are a lot of phase changes going on here, and we're going to fill out this chart. So in your notes, I want you to kind of do something similar. You can pause the video here and set up this diagram, and then we're going to write above the arrows. Okay, so some of them we've already done. If we have a solid turning into a liquid, that's kind of like ice cream turning into liquidy ice cream. I think that's melting. And that's what I want you to do, is write the words above each one of these arrows. So if you didn't get them all done, pause it here again. All right, so a liquid turning into a solid, that's freezing. A liquid, kind of like a puddle, turning into a gas, that's evaporation. Now a gas turning back into a liquid. So what I would think of here is like, imagine, you're kind of in a steamy place like the shower, and water droplets, they're not a gas anymore, they become a liquid like on the mirror. That's condensation. You see that a lot like on the grass in the morning, because the liquid water in the air condensed and it made little droplets on the grass. And then the two hard ones, a solid turning directly into a gas, that one was the sublimation one. That's the dry ice, right? And a gas turning back into a solid is deposition. So those are the two hard ones. I think those are really hard. So let's try this out. I do think you should know all the common phase changes. Maybe these last two down here, it's okay if you don't know them. But let's try this out. Let's try condensation. If we wanted to know, is condensation, I hope you're okay if I abbreviate, is condensation endo or exothermic? I want you to pause the video here and look at the particles before and after and decide whether they have to gain or lose energy. So what did you come up with? Which of these two are moving faster? Well, gas particles are always moving the fastest. They have a lot of energy. And if you're going from a gas and you're going this way to condensing, these are moving slower because liquid particles move slower. Well, do we have to gain or lose energy to make fast things become slow? I think you're going to have to lose energy. And if you're losing energy, it's like losing money. Q is positive or negative? I think it's negative. Heat is going to be leaving, it's going to be going out, it's going to be exiting. So it's definitely exothermic. All right, that's lesson 2. There will be an assignment after this so that you can check your understanding, but great job today.